Here we go. Okay, welcome everybody to our weekly seminar series. I hope that everybody is safe and sound, considering the very hard situation we are passing through. And we are very honored to host here Dr. Yannick Garcin from CERGE-IRD in Aix-en-Provence in France. Yannick, thank you very much for coming. Merci beaucoup.
Thank you.
And Yannick is a researcher at the French National Research Institute for Sustainable Development, which is the IRD. It's based in Serge in Aix-en-Provence. His work is based in paleoclimatology and geochemistry and focuses on the environment and climate of sub-Saharan Africa, particularly through the study of terrestrial sedimentary systems like lakes, pits, and cave sediments. He analyzes environmental, climatic, and anthropogenic tracers using mineralogical, geochemical, and isotopic tools such as plant walk, VAX, delta D composition to reconstruct the vegetation, soil conditions, climatic variability, ITCZ, monsoon system variabilities, and human impact like deforestation and agriculture. His research spans from past climate cycles to the present, with the focus on Central Africa, in Gabon, Cameroon, and Republic of Congo. So with these words, thank you very much again for coming here and join us. And today is going to show and present a presentation entitled Threats to the World's Largest Tropical Peatland, Insights from the Past. So thank you very much.
Okay, thank you. So, hi everyone, and thank you very much, Nicola, for your invitation. So, I'm now going to talk to you about climate change and carbon cycle in the peatlands of the Central Congo Basin. So, the main object of this talk is peats. Peat is organic-rich type of soil. So here in this picture, you have a sample of peat from the Congo Basin. You can see it's very dark, meaning it's very rich in carbon, and it has a lot of plant debris. You can see here, for example, kind of rootlets. You will have some fibers, etc. So the peatlands, they occupy only 3% of the Earth's continental surface. But we know that they store 1/3 of the soil organic carbon. And so they are a very important link in the biochemical cycle of the carbon. So in the peatlands, the plant remains, they decompose very, very slowly because they are stored in oxygen poor condition as long as the peat remains covered by water. And so in the peatlands, generally, you will accumulate organic matter and carbon for millennia. What you see in that map is that the peatlands, they are predominant here in the northern hemisphere high latitudes, where the low temperature and the water saturation, they are preserving the organic matter from decomposition. In the tropic, despite warm temperature, we can also found some peatlands which store like a significant carbon stock. And the presence of the peatland in this region is due to the chemistry of the plants and of the pits. We know that the peatlands in that area, they are containing, for example, more aromatics compounds and less carbohydrates in comparison to the peatlands, which are here in the northern hemisphere high latitude. One very important fact is that the tropical peatlands, which are in that region, they are the most efficient terrestrial carbon store on Earth. And they are containing about 20 times more carbon than per hectare, than the tropical forest, which live on top of this peatland. So here in this presentation, we're interested in this object here. This is the same object on that map. So it has only been described and mapped very recently in 2017. And according to this study, the peatland of the Central Congo Basin will store about 30 gigaton or petagram of carbon on an area which is about 170,000 square kilometers, which is about the size of Tunisia, for example. So it is, according to the study, these peatlands are the largest tropical peatland complex on Earth. So on this map here, you can see the extents of the peatlands, and on top of this, you have some overlain, some polygons, which represent future planned human activity in the area. So to date, the history of this peatland and the associated carbon dynamics is unknown. However, the knowledge of this history is necessary to determine the vulnerability of this peatland to climate change, and also to help to guide policies for oil and mineral exploration, logging, agricultures. All of these activities will threaten the peatlands, as you can see on this figure. So there are a lot of activities which are planned for the future in this region. So to reconstruct the history of these peatlands, we went to the Republic of the Congo and the Democratic Republic of the Congo to collect peat cores. So generally, they are very long and difficult field trips. We don't go there for 1 week, but we go there for several weeks or several months. So first, we need to take a car from the capital, the main city, to another city, much remote. We need a 2-day trip. And then we take these little boats there where we will live for several weeks. So we camp during the night on the shore, and then we continue our journey through the peatlands. And then we walk for several days, or depending on the thickness of the pits, and then we collect the pit samples when we find the right location. So in this figure, you can see 3 of the age depth model. So you have the age and the depths of 3 locations that we studied. And you see that these locations are located all across the Central Congo Basin peatlands. So these 3 cores are about 6 meters long and cover a time frame of the last 20,000 years, more or less. What you can see is that in the 3 pit core, between around 7,500 BP and 2,000 BP, we have a very strong change in the slope of the age-depth relationship, which is 5 to 8 times shallower than for the pits directly above and directly below. And we call it this interval the ghost interval because it represents an interval where the pit was there before, but today it has largely disappeared. So this study was made in 2022, and it was featuring these two cores here, this one and this one. And now we have also other study that we published in 2025, and where we present other pit core, this one, and this one. And what is very important that all these new studies strongly supports the fact that the ghost interval was a widespread phenomenon. So at the scale of the Central Congo Basin, you see this very marked step here, 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 and here. What are the causes of this ghost interval? So we are proposing 4 scenarios. The first one is secondary physical erosion of previously accumulated pits, for example, by fluvial erosion or anthropogenic disturbances like agriculture, slash and burn activities. The second hypothesis or scenario is the reduced litter inputs and new pit formation. The third scenario, it's the increased contemporaneous decomposition following, for example, a gradual climatic drying, for example, starting at 7,500 BP until 2,000 BP. And the last one, scenario 4, is secondary decomposition at 2,000 BP due, for example, of an abrupt drying event. So what about scenario 1, secondary physical erosion? So this figure presents you 2 HDF models from 2 locations, one here and one here. So they are all 2 located 300 kilometers away. So they are not very close. And what you have here is the ghost interval. And on the 2 HDF model, you can see that there are some radiocarbon edges which are right in the middle of the ghost interval, here and here. And so this intermediate edge, in fact, they suggest that the secondary removal is unlikely, and this falsifies scenario 1, because if there have been erosion, you will see like an erosional unconformity, and you will never have like an intermediate edge. You will have just a very sharp step, which will mark a hiatus. What about scenario 2, which is reduced litter inputs and the formation of a new pit? So this figure shows you the pollen concentration on depths. And you can see that there is a marked increase in pollen concentration right across the ghost interval. So this is not consistent with reduced litter inputs and reduced pit accumulation. And this falsifies scenario 2. Because if you have an increase in pollen concentration, that means that you have an increase in the vegetation productivity. And so it's completely the opposite of a reduced litter inputs. So our results, they indicate that only these 2 scenarios there are possible: increased contemporaneous decomposition and secondary decomposition. So here I show you a figure which is a bit complex, but we will go slowly to explain it. So you can see the stratigraphy of the main pit core we studied, which is the core CN174. And you can see the geochemical proxy, which are classified according if they are affected by decomposition, they are in red, so they are this one. And if they are not affected by decomposition, they are the blue one here. You can see that there is a dip here in the E index, which was measured by Roqueval techniques, and which is indicating organic matter decomposition, especially the labial phase. of the organic matter during the ghost interval. You have a spike in the total organic carbon, and you have a spike in the nitrogen to carbon ratio. At the same moment, you can see a dip here, more negative delta C13 value for the bulk organic matter here, which is indicating organic matter decomposition. Conversely, the delta C13 value from the long chain alkanes here, which are recalcitrant molecules, do not show any changes during the ghost interval. So this really indicates that some organic matter was decomposed. So this is another diagram which are showing you the rock level data, and we present it because it's allow us to evaluate the degree of decomposition of the organic matter in the pits. So the x-axis here represents the total organic carbon. So you see there is a wide range, and the y-axis represents the E index. And you see when you go to higher value, you have more preservation of the organic matter, and lower value, you have more decomposition. The Congo pit data, which are here, the dots, they are compared with reference material from Gabonese litter, so from the Gabon, so topsoils, and from lignites from India. What you can see is that during the ghost interval, there are the red dots here. The E index decrease and the total organic carbon increase to values which are similar to lignites, which suggests that the pit was extremely degraded. So to elucidate the causes of this ghost interval, we used gas chromatography isotope ratio mass spectrometry technique. So we use this device here, which we call GC-RMS, and we extracted the soluble organic matter from the pit. We separate different organic fraction according to polarity. We purify them, and then we inject them into this machine. We measure the hydrogen isotope of the long chain alkanes, which are molecular fossil of past precipitation. The carbon isotope here, on the same molecules, they are providing us information about the photosynthetic pathway of the plants, and then about the vegetation cover. So today, the studied pit here is about 6 meters deep or thick. So we estimated that during the ghost interval, we lose about 2 to 4 meters of pits. So when you look at this diagram, you can see that between 5,000 BP and 2,000 BP, you have a gradual increase in the delta D value of the plant waxes. Keep in mind that the scale here is inverted. And this gradual increase suggests a gradual drying of the climate, which has lowered the water table and exposed the pit to the open air, leading to the mineralization to carbon dioxide. So in addition to this contemporary decomposition, we see that the pit which was deposited here during wet interval is also degraded, which suggests that there was also some secondary decomposition process which were active in the pit core. The vegetation, which is here, is also impacted by this drier period, as the contribution of pollen from tree taxa that are characteristic from the tropical peat swamp forest here decline. And it's really follow the trend as we see in the paleoclimate record. When the climate stabilizes again during this period, the swamp forests developed again and the peat started to accumulate again. So using the isotopic data we produce on this pit core, a global calibration of the soil delta D data with the delta D data of the precipitation, together with climate data. Here you have the seasonality index and the precipitation amounts at the global scale, together with the relationship between the rainfall amounts and the delta D of the precipitation at close location from our sites, we were able to reconstruct the past precipitation regime. So we were able to do this because in this region of Central Africa, as you can see on this figure there, the delta D of the precipitation is strongly controlled by the precipitation amounts effects. That means that there is a depletion in deuterium of the precipitation with an increase of the amount of precipitation. So in this figure here, which is a bit complex, I will try to explain. You have what we call the climatic space of the tropical peatland. In Asia, here, this is the green color. In America, here, this is the blue color. And in Africa, here, this is the orange-red colors. On the x-axis, you have the annual precipitation, and in the y-axis, the seasonality index. So when you go to higher value of seasonality, you increase the seasonality. And when you have a low value, you don't have a seasonality. Meaning, for example, here you are at the equator, where it's rain all along the year. And more you go toward higher value, you have more monsoonal climates, where you have a short rainy season, but intense rains. What you can see on that figure is that the current peatlands in Central Africa, in the Congo, they exist under a climate that is considerably drier than the other tropical peatlands. Now, on the same figure, we put the solution for precipitation amounts and seasonality, which are derived from the delta D value of the plant wax in the core, both for the periods before the climatic drying, so there are these dot lines, and at the end of the drying trend at about 2000 year BP. They are the plane lines here. We observed that the climate space occupied by the Congo peatlands prior to the drying, that means here, okay, overlap with the same climate space occupied by modern peatlands in Southeast Asia and America. While today it is much drier, and it was even drier 2000 years ago. So when we look at the climate models, they do not really agree that anthropogenic CO2 emission will lead to longer droughts in the region. you have three scenarios there with 1.5 plus temperature, 2 degrees, 3 degrees, and you see that the response of the temperature rise in Africa is very clear. But when you look at the response of the mean annual precipitation change, in all three scenarios, you have a very low confidence in the direction of changes. However, the climate data from the recent decades that you see here show that the length of the dry season, here of dry season length, is increasing, which suggests that in the future, if these trends continue, the peatlands may be approaching their tipping points. So the take-home message from this first part on the paleoclimate is that our study indicates that the peatlands of the central Congo basin are vulnerable to climate changes. And our study also suggests a positive carbon cycle feedback. If the anthropogenic carbon dioxide emission cause climate-induced drying in the Congo basin, then this will trigger the release of additional carbon from the pit to the atmosphere, hence contributing to global warming. So together with climate, human impacts on this ecosystem may have varied through time. In the figure here, you see a recent compilation of C14 data from archaeological sites in Central Africa. What is clear from there is that there is a marked rise of the human activity and occupation about 2,500 BP, which is often related with the settlement of the Bantu-speaking people in the region, which is accompanied with technological developments such as agriculture and iron metallurgy. So past human activity may have also impacted these peatlands. During our fieldwork in 2022, and with the help of a drone and some satellite imagery, we observe a very high concentration of this structure in the landscape, which are ancient raised fields at the border of the peatlands. So the peatlands, they are just lying here, just very close by. So this agricultural structure, they are clue of past human activity on the peatlands in this region. So in the very near future, we will study them with archaeologists in the frame of a new funded project that will represent the PhD thesis of Samuel Kayes, which is shown here in this photograph. And the fieldwork will start next month. The question regarding this man-made structure are the following. What are their age and their function, their architecture, their area, the superficie, the factors that contributed to the rise and their decline, and what are the impacts on the surrounding peatlands and the regional carbon cycle. Finally, this study is a result of a collaboration between several groups from many institutions in 8 different countries and supported by various research grants. Thank you. I'm done. So I can't hear you. So maybe
okay, you know what? Thank you so much. I'm not sure if Nicholas is able to proceed. Nicholas, are you still here? I think not. Okay, well,
Very good.
first of all, thank you so much. This is a really fascinating topic, and I think for many of us, since we're usually dipping our feet in the sea, it's nice to get out of the ocean a bit and look at some of these processes. Um, so what we do at this point is, of course, open to questions. Many times our students can be a bit shy, but if anyone would like to ask some questions, this is your chance. Doesn't have to be the Guinness Book of World Records question. You can ask everything from field work to methods, anything that you're curious about. Yannick won't bite, I promise.
No, no problem. I will try.
Sometimes I have to warm them up, especially on Zoom.
No worry. I think this is common to every student. Huh?
Yeah. Well, I have questions. I'm happy
Yes.
to kick it off.
Yeah, go for it.
And also, if anybody wants to put a question in the chat, that's fine, and I'll ask the questions even anonymously if you'd rather. So I'm just curious. I come from a perspective. I do a lot of work just on accumulation and sedimentation rates and things like this. And so what you were showing about the ghost interval,
yes,
is pretty fascinating. I guess I have a couple of questions. One, and maybe you mentioned it, but you were talking about how the pollen the concentration of pollen is quite high.
yes.
Is it possible, is there a way to calculate or to consider that because pollen is, and maybe it's different there, but generally pollen is, of course, wind delivered. Is it possible that it's sort of just a proportional thing? Like there isn't as much accumulation of, say, the vegetation, so it's appearing as if the pollen relative to the amount of sediment that you have there. Does that make sense?
Exactly. In fact, what we think is when you look at this curve here, it's like the peak is there because the time is compressed, in the sense that there have been a lot of decomposition. And so the pollens, because they have these layers, I think is exin. It's kind of like a layer that protect them to decomposition. I mean, the alteration. So they are quite resistant. And this is why we can find them in rocks, in million years old sediments. And so here, what we have is probably the level was the true level was probably much lower, maybe at 2, for example, on that scale. But the spike is there because the labil organic matter is gone, and then it make an effect of concentration on the pollen. But in that case, if for example there was been reduced liter inputs, we will probably go to value close to 0. But this spike is there because a great part of the organic matter is gone because it has been alterated. So, but this is clearly the aspect of the spike there is related from the decomposition, but because we have also some value which are like remain high there, either if you probably uncompact this area there, you will still have a significant amount of pollen. So if you expect that you have low liter inputs, then you will probably have much lower value. We also have some other pollen data which are not related to the concentration of the pollen grain, but about the distribution of the pollen taxa. And what we have there during the whole Holocene period, which is cover all this core here, or all this interval here, what we have is that we see that the vegetation remain a very well-developed tree vegetation. There was not any shift between, for example, tree to savanna vegetation, forest to savanna. It was clearly like a closed forest, but we see that there is a change in the contribution from certain taxa, okay, change in the composition, but we remain like a closed forest. So, I mean, so if there is no change in the main state of the vegetation, you are still in a closed forest. You are not expecting any change in the litter inputs because you keep a forest, you know.
Mm-hmm. Okay, I did get a question privately.
Yes, go ahead.
Okay. Let me read this here. Okay. So, how is the input, the moisture, like the moisture in the peatlands, in these tropical peatlands, how are they different in terms of their source, like rainwater versus groundwater from other parts of the globe?
I mean, you mean the source, the moisture source?
Like the moisture that's created, I think if I understand the question, it's, peatlands generally require,
Right.
higher moisture. So and some peatlands, it's dominated by rainwater, like the bogs.
Completely.
Yeah.
Yes. Oh, that's a very interesting question. So
Yeah.
when you look at that map here, you have this black area here, color represent the Congo River. Okay, and on that side here, most of the pits are considered ombotrophic, which mean that they are growing because the source of the water is only precipitation. On that side here, along these rivers, for example, there are minerotrophic pits. And the main source of the water is the groundwater. Okay, so they are very two different functioning of the pits. But what is very interesting is that also these pitlands, they are very different in terms of setting. We do see in the two of these, one this side here, they are ombotrophic pitlands, and this one minerotrophic peatlands, like fluvial, like they are fluvial dominating peatlands, and here is rainfall dominated peatlands. And you see exactly the same pattern, in terms of peat accumulation on the two.
Oh, yes. Anyone want to ask a question before I go to the next one? Okay, do we have time for more questions, right? Oops, where's my timer here? Okay, there's another question here, which is make sure I understand this. They asked about the distance between the sites, but I think we can see it's a few hundred kilometers between each of those sites, right?
Yes, where there is around, like between these two, there is 300 kilometers.
So, oh, here, okay. Another question. This about the ghost interval again.
Yes.
So the question is, and you could tell we're from a marine oriented program. When you compare it to sea level changes,
Yes.
so imagine you've looked at that. What can you say about this relationship of global sea level changes in this ghost interval?
Well, yeah, we have looked at the sea level and tried to make to make a comparison, or propose an hypothesis that may be an impact, but we haven't found any relationship or compared to the sea level. I mean, we look at that also. We have some peatlands. We have now a more complete record of the peatlands back in time, and we also compare it to the global sea level change because I mean, there are more variation at the scale of the glacial interglacial time scale than at the scale of the Holocene. So, I mean, the variation we observe in the sea level during the late Holocene, they are not as high as during a glacial interglacial transition. But we could not find any, I mean, significant relation between the two variables. So we have not taken the sea level as a scenario to explain the observed changes.
What's the oldest peat record? No, this is my question. How
in this region or in the world?
In general, but definitely in this region.
I mean, when you look at the actual records in the tropics, for example, I think we dated some pits in the Congo at about 40,000 years. We published recently a paper on that. And
40,000,
yeah, 40,000 years, yes. But
okay.
But
Nice.
I'm sure that the pits are much older. And what is happening here is you have a cycle of deposition and then decomposition or physical erosion, and they are gone. But what is very interesting is that some people have been working in some very long marine record of the Congo, the marine Congo Delta. So they have like very long record, and they have looked at some biomarkers from bacteria, which are I think using methane. And so what is very interesting is that you see very well that these bacteria are present today because of the current peatlands, but there are cycles in the past where they were also there in high concentration, and this probably is a signature of the presence of these pits in the past. But now the pit they are gone because the pits, they are not rocks. Maybe when they are like shifting through lignites, they are harder, and maybe they are more preservable from physical erosion. But now the pits, they are easily erodable. You know, they are not like cohesive material. So it's very easy when you have a very, very dry period that physical erosion can make them all gone. So probably this area is flat. The central Congo basin is extremely flat, very large, and it has probably accumulated peat for hundreds of thousand years, maybe million years in the past. But we don't have any more the record because all the peat was eroded through climate cycle, through the deep marine basin offshore the Congo coast, you know, so the Congo River canyons. And then I think in the future, there will be studies which will try to link very precisely the accumulation of pits in the area based on marine records.
Excellent.
I'd like to ask a question if it's possible.
Great.
Yes.
Itzhak, please.
Yeah, a couple of questions. First of all, thank you very much. It's a very interesting talk indeed. You opened some windows I wasn't even aware of. I'm a little confused. Basically, we think that the ghost interval reflects diagenesis of peat, right? I mean, we think that this interval reflects something that happened at the end of that time and not at throughout the time, right? I mean, when do you think was the time window that actually, can you?
Yes, I think we propose these four hypotheses here, but we believe that the two occurred. I mean, there is one which is contemporary decomposition and one is a secondary decomposition, meaning that we believe that it's occur during this gradual drying here, which is a period of about maybe 1,500 or 2,000 years, okay, and that may be maybe the maximal of decomposition maybe occur at the end. So it's together, you know, but with the proxy we have, we cannot go further. We need more information, and we have also some project to work on marine records offshore the Congo and try to see, because the Congo deep sea fan accumulate the history that is already gone on the continent. So making the link between the two, maybe we will be able to really provide a clearer story of what's happened there. We need more data because the carbon in part of the organic matter and the carbon is gone. So is why it's a ghost interval. And so we need to take the data maybe in an accumulation place, for example, a deep basin which accumulated this history that is going to vanish today on the continent.
Right. Yes, that was one of my next questions. Indeed, that you need to call the Congo fan, but this is it's a major element. I don't know how much, although much work was done on it on the last years. There's a major element there. I don't know how much where are the past accumulations. But what you're saying is that basically there was a time, 2, 3, 4,000 years ago, that these pits degraded and released CO2 to the atmosphere. Do we have any indications of this happening from elsewhere, or the significance or the implications of that?
No, in fact, we tried to look, for example, at the high score records, if we could see, for example, in the CO2 concentration a spike, but it's not possible. I mean, if we will see a spike, I think we calculate that it should have happened at the scale of some decades, which is a very short time scale. But if it's at the scale of a millennia, it's too slow to see really an imprint in the global CO2 atmospheric record. So we don't have any other evidence, for example, from an archive elsewhere that this event occurred. No, we don't. This will be like the smoking gun if we'll find that, but no.
Yes. This is very significant to look at that if we want to talk about the future, about the implications to the future. Now, it seems like those curves are very similar to our curves. I mean, they reflect the wet, the sapropel periods, and the wet periods of the Sahara are the same wet periods that you're seeing here. So we're seeing the tropic, seeing the same wettening and drying that we see further to the north in the Sahara belt.
Yes.
So it's not that simply the monsoon belt moved northward, it intensified.
Yes, exactly. I agree with you. Yes. This event they're around like at the early Holocene. I think this is the most the wettest event we have recorded in the region, and it's correspond to the sapropel.
Right.
Yeah. So yeah, it's there is a common climate in the tropics and subtropics related to monsoon, but not only the migration of the rain belt, but it's probably the intensification of the precipitation in the wall belt.
That's an important point. Yeah. Thank you. Very interesting.
Thank you.
Hold on. Any other questions? I have more questions, but I think we're getting to our maximum hour here. One more question? Okay. Thank you so much, Yannick. This was really, really fascinating. I definitely this is very, very relevant, seeing these global patterns and how everything kind of ties in together. It's a really, really amazing, and like Itzhak, said, kind of opened up our eyes to a completely different angle and location and environment where we can see these things. So we appreciate your time and hope that, well, you're very safe in France. Continue to enjoy that. And we hope that we'll have more connections with you. I'm sure Nico's put you on our list so that if you'd like to see, what lectures we have going on, and we do record most of them. So you're welcome to, and I hope you'll take a look at some of our other lectures. So thank you so much for taking the time and giving us this amazing presentation.
Thank you very much. And yes, I will follow the seminar. I've seen that there is a links there, and I will see there are many very interesting topics. Then I will continue to watch more of this. Thank you very much, and take care. And yeah.
Yeah. Thank you. Bye-bye.
Thank you.
Bye-bye.